Good morning to all of you. I am Moez and today we are discussing about class 12 physics chapter number 12. In this lecture we will be discussing about the electron orbit. First of all, electron orbit. What is it is electron orbit? Why we are required the electron orbit? But first of all, we just know about the electron. After that, what Hans or Hans Marsden or Hans Geiger, two students of the Rutherford was described the Rutherford nuclear model. So due to this Rutherford nuclear model, what we will get? We will get that there is a due to this phenomena we can get the electron. It is a nucleus. It is in a center. Something in the positive charge is there. Okay, and something is there. So due to this phenomena, all these particles, one of the 10 raised to 4 particle, one out of 10 raised to 4 particles of alpha particle in the backward directions. So why then due to this phenomena we can get assumptions of this phenomena, and due to this phenomena we will get that there is a nucleus. In the nucleus something is there. So due to the nucleus there is he was giving to the whenever it is a nucleus, on that time electron it is in a orbital motions. Electron it is in a orbital motions. Now electron, whenever electron it is in a orbital motions, so on that time Rutherford was given to us when it will be going in this directions, it is a look like a spiral form. So and on that time he was also told whenever it will be moving, electron is moving around the nucleus, on that time there is a energy will be produced. But if the energy will be produced, it will be atom will be not be stable because it will be going to the nucleus. So due to these assumptions we can it is a failures of Rutherford, but due to these assumptions we can say this is a it is electron is motion in look like a spiral form. But see here, what is that electron orbit is that, and Fe it is a force of the our force is that. Okay, it is our force is that. This force is known as the electrostatic force of attractions. Electrostatic force of attractions. So it is represented as Fe. This is a represented as Fe. And now again, what is that? It is a Fc. What is the Fc? Fc it is our it is a centrifugal force to provide the nucleus, provide the requires the centripetal force. It is a represented as Fc. But see here, mv square upon r, it is equals to 1 upon 4 by epsilon 0 e square upon r square. So see here, mv square, we know the our centripetal force is that mv square upon r. So due to this phenomena we will get that thus the relation between the radius and the electron velocity is that. So see here, what will happen, we will cancel out these things. Okay, this r and this r, so we can make the common mean of this equation. It is r. So r it is equals to what we will get, r it is equals to e square upon 4 by epsilon 0 m by m into v square. So see here, this our r it is equals to e square upon 4 by epsilon 0 m into v square. So this is a radius of, and it is a related relation between the velocity. Okay, see here how it is related. R it is proportional to 1 upon v square. When the velocity will be changed, the radius will be changed. R it is equals to 1, r is proportional to 1 upon v square. So this is our radius. This is the relation between the radius and the electron velocity. Okay, so now the kinetic energy of K, the electrostatic potential for for electron in a hydrogen atom, it is equals to K, it is equals to K over what is the K? It is our kinetic energy. So K it is equals to 1/2 mv square, and also it is equals to e square upon 4 by epsilon 0 into r. What is that? It is equals to this is our e square upon 8 pi epsilon 0. It is our mistake is that 8 pi epsilon 0 r. Okay, on half mv square it is equals to e square upon 8 pi epsilon 0 r. Because of m 1 by 2, so we are multiplying this here. So due to this phenomena we will get that the 1 upon 8 pi epsilon 0 into r. Okay, so see here, and also again what is that, we will get that the potential energy u it is equals to minus e square upon 4 pi epsilon 0 into r. Okay, what is that? It is equals to minus e square upon 4 pi epsilon 0 upon r. Now but see here there is a negative sign is there. What is that? What is the negative sign is there? The negative sign is u is significant that the electrostatic force is the minus r direction. What will happen? It is in a opposite direction. So minus r direction. So that's why what we are taking as a minus sign is that. Okay, so that's the total energy of E. Total energy of E is equals to what? E is equals to kinetic energy plus potential energy. So kinetic energy is that E square upon 8 pi epsilon 0 upon r, and the potential energy is equals to minus E square upon 4 pi epsilon 0 into r. So see here E is equals to minus E square upon 8 pi epsilon 0 into r is there. Okay, what will happen? We will get that the again minus E square upon 8 pi epsilon 0 into r. So see here this is our total energy of electron. Okay, total energy of energy is that, but see here again there is a negative sign is that. So electron is negative, so it implies that the electron is bound to the nucleus. What will it is says that the electron is bound to the nucleus. If E were positive, the electron will not follow the closed orbit around the nucleus. What will happen? E were positive and electron will not follow closed orbit around the nucleus. So it means there is a no close, not around the closed loop or closed around the nucleus. Okay, so see this is our topic is that. Okay, now what we are taking? We are taking another topic is atomic spectra. Okay. But first of all, we understood the atomic spectra. What is the atomic spectra is there? So we know that whenever the light is coming from outside, so due to the electric discharge, whenever the atoms are excited on the time, there is something energy, something lights, something will be pass coming from outside. So on that time what we will get? We will get the spectra. Okay, we will get the spectra. So this is our spectra. So we are talking about that the atomic. Now we are talking about that the atomic spectra. Now see, we are talking about that the atomic spectra. So first of all, why we are requiring the atomic spectra? So whenever see here what figure I shown the one figure is there. Okay, so there is a something atomic gas is coming from outside in the air. Okay, and now there is this one slit is that, look like here. From this rays it is passing from this instrument, and also it is a one type of prism. So this rays is coming from here, and we will get that the spectra, atomic spectra. Okay, from these equations we will get that the atomic spectra. Whenever with the atomic gas, okay, whenever the atomic gas, it is a atomic gas vapor is excited again at a low pressure, usually by passing an electric current through it, the emitted radiation has a spectrum which contain a certain specific wavelength only. It has a certain specific wavelength. Okay, it has a certain specific wavelength is there. And it is a discharge due to the discharge tube. So we will get the specific wavelength is that a spectrum of this kind is a term as emissions line spectrum, and it is consist of bright light. Okay, see this is an emission line spectrum. Whenever we see here this is due to this phenomena we can see the one figure is there. It is a look like, see this is like a band. Okay, this is a band, and all another is that it is a absorption spectra and emission spectra. There is a two types of spectrum is the absorption spectra and the emission spectra. So we can see there is a consisting of the bright lines on the dark background. The spectrum emitted by the atomic hydrogen is shown in figure. See here, this is a dark line is that. This is a dark line of the spectrum. Due to this phenomena we will get this like this in the spectrum. So see here, this is a dark line. So study of the emission line spectra of material can therefore serve as a type of fingerprint like that. In the mobile phone, you have shown that whenever your finger, adding your finger on that time, you can see the black line is there. Okay, there is a something black line is that look like that. Okay, as look like that. So this is one type of the emission spectra is there. Okay, this is a one type of emission spectra is there. So due to this phenomenon, we will get that the emission spectra. Due to the emission spectra, we can get that the dark line is there. Okay. Now see here the dark line spectra. The dark line corresponds to precisely those of wavelength which were found in the emission line spectrum of the gas. So this is called the also absorption spectra of material of the gas. What when the whenever the dark line corresponds to precisely those wavelengths which are found in the emission line spectrum of gas. This is called the absorption spectrum of the material of the gas. Now see here when we are talking about that the spectral series is that. This is a spectral series is that atomic spectra. It is our spectral series. There is a 5 type series is that Foxtrot, Lyman, Balmer, Paston, Brackett and Fund. So it is very easy to remember that. What is that? It is a very easy to remember that. It is a very simple logic is that lie papa breakfast. We are talking about, we are remember as a lie papa breakfast. So see here lie it means lemon, ba it means balmer, pa it means passions, bra it means bracket and fun fast it is a fun. So that is a very easy to remember this. So lie papa breakfast. So there is something is given to us. This is a spectral series is that how we will get we might expect the frequency of light emitted by a particular element would exhibit some regular patterns. Hydrogen it is the simplest atom and therefore has the simplest spectrum is that. Okay, what will happen? There is a hydrogen in the simplest hydrogen it is the simplest atom is that, and due to this simplest atom it has the simplest spectrum is that also. Okay, so what will happen? So so it is observed spectrum. However, the first state there was not seen to be any reassemblance of order regularly spectra lines, but the spacing between lines within certain set of the hydrogen spectrum decrease in a regular way. Okay, so each this set is called the spectral series. So suppose see here this is a spectral series. After that something there is a band, we will not get the band. So after this is spectral series, but so after suppose here again what will happen? There is a spectral series. So this is this band is not given to any kind of lines. So this is a due to this phenomena we can separate this spectral line. Spectral series is that. Okay, so Lyman, Baba, breakfast. So Lyman, Baba, passion, bracket and fun is that. So see here now first of all. See what will happen? There is a Balmer. What was a Sweden school teacher was that Jacob Balmer. It was a school teacher. Invisible region of the hydrogen spectrum. The series is called the Balmer series. Okay, due to the hydrogen spectrum, the series is called the Balmer series. The line with the longest wavelength, it is the 656.3 nanometer. In the radian is called the H alpha. In the red is called the H alpha and the green is called the H beta. So the third line of 431. See here there is something is that here see here suppose it is a look like that. There is a 364. This is our H alpha. Where is H alpha? It is our suppose it is our H alpha and it is value is that how much is 656.3 nanometers. Again then suppose it is our H beta on that time it is a 486.1 nanometers. Then again what will happen? H gamma. Due to this phenomena we will get that the H alpha, beta, gamma, delta and rho and also infinity is there. So this is the wavelength decrease. As the wavelength decrease, the line appear close together and weaker in intensity. Balmer found is a simple empirical formula. So Balmer found the simple empirical formula. It is equals to 1 upon lambda. It is equals to 1 upon lambda. It is equals to r into 1 upon 2 square minus 1 upon n square. Okay, so it is a simple formula. Is that what? Where here? What is the r? R it is a constant. It is called the Rydberg constant. Okay, it is called the Rydberg constant, and the value of r it is equals to 1.097 into 10 raised to 7 meter. How much is that? Value of r it is equals to 1.097 into 10 raised to 7 meter inverse. It is our Rydberg constant. Okay, it is our Rydberg constant is there. So this is our first series, Balmer series. We are talking about the Balmer series. Then after, what will happen? See here, there is a Balmer series is that. So the Rydberg constant is that, and also whenever the which is get the continuous spectrum, okay, spectrum wavelength, due to this, whenever we are putting the value of n it is equals to 3 4 5 and it is equals to 3 4 5, so on that time we can get the answers of that. So again we can got, okay, what will happen, there is another scientist are also there, so he was also describe another empirical formula for this represent the formula. So see here, there is a Lyman series is also there. What is the Lyman series? Here, what is the lambda? Lambda is a wavelength. Okay, so 1 upon lambda is equals to r into 1 upon 1 square minus n square, 1 upon n square. It is here, and we have put the value of n, it is equals to 2 3 up to infinity. Then after, what will happen, there is a partial series is also there. So partial, it is a scientist name, so it is also gives the 1 upon lambda, it is equals to r into 1 upon 3 square minus 1 upon n square. Here what we will get that the n is equals to 4 3 up to n. So now then again, what is the bracket series? In the bracket series, here see here only one thing it will be changed, 2 3 4, and again see here 1 2 3 4 and again 2, and also last in this last equation, what we are all above, we can simply with making one simple equation is that 1 upon lambda is equals to 1 upon m square, it is minus 1 upon n square. So see here, this is our bracket series is that 1 upon lambda is equals to r into 1 upon 4 square minus 1 upon n square. Here what is the n? Value of n, it is equals to 5 6 up to infinity. Again now last is that last but not the least, fund is there. Fund series is also there. So it is equals to 1 upon lambda, it is equals to 1 by 2 and 1 upon n square. Here and it is equals to 6 to 7 up to n. All, so this is our common equations is that standard equations. We can also say 1 upon lambda is equals to 1 upon m square minus 1 upon n square. So due to this series, what will there is only few element of wavelength singly ionized helium, and the doubly ionized O spectra can be easily represented by a simple formula like these equations. Okay, so wavelength and the hydrogen atom are radiated or absorbed. So however, these results are empirical and do not give any reasoning why only certain frequencies are observed in a hydrogen spectrum. Okay, so see, this our topic is that. I hope you understood this topic. It is a very easy topic to remember that. So I hope you understood this topic. So I thank you guys. If any kind, I hope you haven't any kind of doubt in this lecture. But if any kind of doubt, then comment in the comment box. Thank you guys. Thank you so much.